Welcome to our monthly Lunch and Learn. We're very excited about this one, introducing you all to the new Biosolids Emissions Assessment Model, or BEAM. Here at NEBRA, we still believe in climate change and the ability of our industry to reduce our impact on the climate. WRFs are a not insignificant source of greenhouse gases, especially methane, with significant impacts from solids handling processes. So this BEAM tool you can learn about today can help you get a handle on greenhouse gas emissions. So just a couple of housekeeping items. Everyone's muted. Just please stay on mute, but I think I can unmute you at the end to have a discussion and ask questions. We're recording this. I will share the recording in the slide deck with you early next week. There is a Q&A function at the bottom and a chat, whatever you're most comfortable with. Go ahead and type in questions as you think of them. I'll be keeping an eye on that. I have to start out with a huge thank you to the Northwest Biosolids Association for the grant that paid for these most recent updates to the BEAM. And this is important work, so we really appreciate that support. I'll be kicking it off this morning, but I'll be joined by the crew from Northern Tilth, who did the work to update the BEAM, and members of the BEAM team are also on this panel. I'm going to give them brief introductions, but they're all on LinkedIn. Andrew Carpenter is a principal at Northern Tilth, LLC out of Belfast, Maine. He was one of the original authors of the BEAM, and he and his company have contributed greatly to the BEAM. Andrew's joined by Romy Carpenter, a nutrient management planner, and also Haley Jean, works at Northern Tilth. And we also have Bill Brower with Brown and Caldwell. He is the chair of our carbon trading committee, which is responsible for managing the BEAM. And joining him is Baojang Lee with Black and Veatch, who is a member of the NEBRA BEAM team as well. So these are all folks that I call BEAM power users, and we're going to learn a lot from them today. So let me get going with some basics on the BEAM then, Andrew. Go to the next slide. So basically, the BEAM is a pretty elaborate spreadsheet, but it was intended to be able to be used by, the average staff at a treatment facility. It is complicated, but it's a great way to get a handle on it. It covers just the solids, but it includes scopes 1, 2, and 3 emissions, as well as biogenic emissions. These are all based, and Andrew will talk about this, emission factors from published literature, the latest research. And you can use the BEAM to come up with a baseline, what your current emissions are. You can compare up to 10 different management scenarios currently. And so then you get to see the impact of doing different processes to manage your solids. So it'll help you understand what's having the biggest impact on greenhouse gas emissions. Next slide. Just a little bit about the background. As I said, Andrew has been around from the beginning. It goes back to 2008 when the BEAM was originally created for the Canadian Council of the Ministers of the Environment. Canada's been way ahead of the US, by the way, on this stuff. So we jumped on that. That was originally published in 2010. And then it languished for quite a while until NEBRA took it over back in 2021. And Andrew's team helped us update it in 2022. And then we did another update in 2024. And our plan is to update it biannually with the latest and greatest. Again, the BEAM is just for the solids processes. So this shows you the boundaries. And you can see the different, the methane emissions and nitrous oxide and CO2 emissions that come from the different parts of the process. All right, next slide. This is going to be Romy, but before you go, Romy, I'm going to do a quick poll if that's okay. Let me launch this poll. I just want to kind of get a sense before we get into this, if you don't mind, what your familiarity is with the BEAM. If you're a BEAM power user like everyone on this panel, or if you're just interested and wanted to learn more about how to use it. Just give it a minute here. All right, thanks for participating in this. We're getting some good participation. And Andrew, I will end the poll. You can see that the majority of folks on this call here are beginners, 82%. All right.
Good to know. Yep.
All right, Romy, take it away.
So as Janine mentioned, we updated the beam in 2024, and we did so with input from a scientific review team. And we went through and updated quite a few things in the model, but I'll just mention some of the more significant updates. Firstly, we updated the carbon sequestration rates for land applied biomass. We initially just had one rate in there, and now we have a range of rates to select from, which represents the range, closely represents the range that's in the literature, and also gives users the option to consider land management and land conditions when choosing what carbon sequestration rate to use. We also updated the methane oxidation and emissions calculations for landfill scenarios based on, again, input from the scientific review team. And we have new nitrous oxide and methane emissions default values, which was from a literature review that the scientific review team did. And we input the newest eGrid values from EPA to reflect the most up-to-date carbon footprints of electricity based on regions across the US, and then we also have the Canadian regions in there as well. And we have integrated an option to choose whether or not fertilizer offset credits are included for biosolids for both nitrogen and phosphorus, which is something that some people choose not to account for depending on what the goals are of the modeling. And I'll just point out that the Beam user guide exists, and it offers a step-by-step instructions for using the Beam, which, as Janine said, there's a lot of inputs in the Beam. It's a thorough model, and we've tried to lay it out somewhat intuitively, but it's great to have the user guide up to reference the workflow that you need to follow when inputting values in the Beam.
Okay, thanks, Ron. Thanks, Janine. So what I'm going to do today is we're going to go through 4 different management option scenarios with biosolids management. I'm going to go through some of the inputs, some of the things I've already put in there, just so I don't waste too much time and you don't watch me trying to misspell things. But I'm going to try and go through this so you have a little better understanding of the process of filling things in. Hang on for just one sec. Sorry, I was trying to do, we've got some printing in the background. So one thing I want to point out, these are instructions, but really the user guide is the most important element to follow when you are trying to use this. It's a long spreadsheet. It can be a little bit clunky at times. Once you get the feel of it, it does become, I think, more intuitive over time. There is sort of some method to the coloring of the cells, which you'll see, but input cells where you're just inputting an actual value have this olive green number. In a lot of cases, we provide default values to the right of inputs that you can use if you don't have that data. Those are in this blue color. We have some, just for the sake of transparency, cells that just show you calculations where we got numbers from. The outputs on it are in gray cells. Those are the values that are actually used in the final sort of summary of GHG emissions. We have areas that are filled in automatically with information from earlier that you've filled in, but they can automatically fill in, but these are cells that can be overwritten as well. So they're not protected cells if you have the data that is better than what is automatically populating, and calculated results are not filled in any way. Also wanted to point out the one of the things that, so from our perspective in making this, one of the things that we really wanted to do was have everything as transparent as possible. So it's not a black box. It's one of the, I think it's one of the largest benefits of the model It's also one of the things that makes the model sort of longer and maybe seem a little clunkier. But this worksheet, the references and assumptions worksheet, is where all of the default values come from. It's very well referenced. It has everything from sort of simple factors like the carbon content of fuels to very much more specific things like electricity use related to dewatering, a lot of different anaerobic digestion factors, including methane loss from combustion. It gets very specific. And this, one of the things, we do have a scientific review team process that we've been doing every 2 years. We've done it twice now. And a lot of that is geared at making sure that the reference values that we have in here are as up to date with the newest science as possible. So it's a dynamic model. It does change as the science changes. And I think that's really important. We have a lot of factors that we know are going to have more data, more research in the future, and we're going to have a more robust model as we incorporate those newer things. So this itself, I believe, really has a lot of value. We also have, say, and I'll just give an example here in the form of, let's see, carbon sequestration, which is a tough one to put a handle on. In a lot of cases, we have default values in there, but we also have, for people that might have research specific to their own facility, the ability to put in your own default value, in this case for carbon sequestration from biosolids land application or composting. So we've built in flexibility, but we do have, I think it's really well referenced, and this, just the reference worksheet itself, I think has a lot of value to it. So let's get into actually filling things in. The first page is the location and process and digestion, because digestion does change a few things in the biosolids train. In this case, I'm just going to say our, so these are olive green cells. They're all input cells. We're going to look at New England today. That's going to affect a couple things in terms of climate, in terms of electricity generation. So we have, as Romy alluded to, we have all the carbon intensities that are published by region in the US, and we have this for Canada as well, it doesn't come from eGrid, in here, so that if you choose the region that you're working in, it will give you the carbon intensity of electricity there, so that will be used in the final accounting. So here we're going to use New England. We could use Michigan. We'd show it was higher because it's got more reliance on coal. And then we do have the option to look at both a 100-year and a 20-year global warming potential. Most greenhouse gas emissions accounting now goes by a 100-year time horizon. That's what we're going to use. In this case, we're looking at, and this is one of the only places where we actually use tons, like short tons instead of metric tons. We have designed this so it's in a metric system. It makes more sense. It's more useful sort of across the board that way. But in terms of inputs, because so many of us in the US think in terms of actual short tons, we do have this initial input in terms of short tons. I'll just tell you that we sort of planned this ahead of time to look at 50,000 wet tons. So it's 11,000 dry tons, and we're gonna, our sort of baseline scenario is looking at dewatering it to 22% solids, gives us 50,000 wet tons. I actually put in a little calculator here. We have a page that allows for project specific calculations. I actually put in a back calculation here to determine the volume that's going into conditioning, because conditioning is one of the things we're going to look at in this one, even though it's usually not a big contributor to the footprint. So we've got 2,700 cubic meters per day. It's going to thickening at 1% solids. So I put that, that's an input there. I kept it in there for ease, and then we're saying that it's coming out at 4%. We can change, you can change those based on what happens at your actual wastewater treatment plant. We also have the ability to have different analyses for the biosolids in there as you're modeling it. And the reason for this is if you're doing anything to the biomass, the biosolids in this case, other than changing the solids content. So if you're changing the volatile solids content, changing the carbon content, mostly through aerobic digestion, anaerobic digestion, or pyrolysis, you can account for this up front and it will calculate all the way through. So our analysis one, and you'll see where we end up using this in the next, in the scenarios data, is essentially assuming that biosolids, the solids content is not changing in terms of volatile solids, in terms of actual dry matter, in terms of carbon content as it goes through the process, just raw biosolids essentially. The second one, which we are going to use in our accounting today, is anaerobic digestion. So we put in a sludge retention time because that's going to impact the amount of energy that we're using during digestion to run the digestion process. You put in a volatile solids destruction content, VSR, 50%. We have something in there for volume reduction during digestion, but most people have suggested that same volume going in comes out. We just have less volatile solids in it. So we're putting a 0 there. And then in this case, we're assuming that they're going to actually get better, maybe upgrade their dewatering when they do go to anaerobic digestion and get 25% solids. So then you see that's going to change the amount of wet mass going through the process. And that's automatically calculated down here. Now, in terms of actual analysis for things we use in the model, which are nitrogen, phosphorus, in addition to dry matter and solids, nitrogen, phosphorus, total volatile solids, and carbon content mostly. We can fill those in for each of these processes. So organic matter content, we actually have some values you could use. Most plants are going to know what these are. They're pretty simple analyses, but we do have some reference values if you want. I'm going to use for total volatile solids, 78% we have over there for unprocessed material. I'm going to use the 4% nitrogen on a dry weight basis and the 1.5% phosphorus on a dry weight basis. And then automatically with that, these values for the anaerobically digested material get updated using the assumption that nitrogen and phosphorus are preserved in the process, but volatile solids are lost, so they get concentrated. You can't overwrite these. I could put a 5% in there and the cell shifts to show that that was an actual input rather than us relying on other data from the plant. Now we've got one scenario that we're going to use here where we're going to show you thermal drying. So that percent, after dewatering is going to change during the thermal drying process. So that's an input that you put down here, 94%. And you'll see how that works further down the line. I realized listening to myself that I'm maybe going a little fast, but Janine, what do you think of the rate here? Are we good?
No, I think it's a good pace.
Okay.
Could you just explain? So you were actually referencing cells when you went to go grab that 78%?
Yeah. So
Okay.
this is, and I'm going to show that on another one where we have blue cells, but that's a good point. Thanks for thinking of that. So then this is something, the architecture has changed over time of the beam, and the order in which we're filling things in has changed as well. So there's I'm most happy with the order that we currently have, looking at the location, the process, digestion early on, like what actually happens to those solids, if anything, through the process, then the analysis, and then the scenarios data. So we have the potential, as Janine mentioned, to compare 10 different scenarios. And we actually have an example of that on the web that the Beam website that you can download. It shows 10 different scenarios all filled in. In this case, one of the things that's changed is we do the first step in filling in the scenario after filling in the short title and the long title for that. This first one is composting, and we're gonna, we have the ability to put in the short title. It'll show up in the tables, but also the longer title to describe what's actually going on. This is going to be undigested biosolids going to aerated static pile composting. We're going to use that analysis one. That's the one that hasn't been digested, pyrolyzed, or anything like that. So essentially the nature of the biomass and the dry solids content doesn't change during the process until we get to composting. And then we want to put an X in all of these different unit processes that are going to apply to this composting process. So we're going to condition and thicken that material. We're not doing aerobic digestion or anaerobic digestion. We're going to dewater it. We're going to compost it. And we need to look at the value of the greenhouse gas impact of the transportation of that compost. Our second one, we're doing anaerobic digestion, that 22-day solids retention time with a 50% volatile solids reduction. That's changed our analysis a little bit. We have less material, higher nutrient content. That's analysis 2. In this case, we have conditioning, anaerobic digestion, dewatering after that. And then we're going to land application, and we want to include transportation. These last two I've kept filled in, so we don't have to go through that again, but we're going to look at landfilling, undigested biomass to a landfill. Actually, this is not incorrect. Undigested biomass to, because we're not drying it in this case, to typical US. Told you guys I wouldn't be typing that stuff in, but there we are. And then in our last one, I wanted to look at also going to a landfill, but the difference if you anaerobically digested, then dried that material thermally, and then took it to a landfill. So I've got those pre-filled in for this last one. We've got conditioning, thickening, anaerobic digestion, dewatering, thermal drying, disposal at a typical landfill, and then transportation. So this is an important one. There are a few things that you will make a difference as you go further down the line in this. This is called the amounts and destination page. We can have the material in any one scenario going to a bunch of different locations. It's probably more functionality than we need, but you have that potential. And so in this case, we're going to composting. We've got 4 main categories: landfill, combustion, and that's going to include pyrolysis, incineration, gasification, and then composting, which we're doing in this case, and then land application. So the main category is composting. The subcategory in this case is aerated static pile. I've already determined it's going to be we're going to account for a round trip because it's not necessarily going to have a backhaul. And that composting, the aerated static pile biosolids composting facility is going to be 150 miles from where it's being generated. Last thing you have to fill in here is whether it's truck or rail. Rail, if you're going long distances, rail transport is quite a bit more efficient from a greenhouse gas emissions perspective. And then in the second case, we're going to anaerobically digest the material, go to land application. So our main category there is land application. In this case, it's not thermally dried or alkaline stabilized. It's not going to pyrolysis. So the category is other, maybe a little bit non-intuitive there, but it's none of those other things. So it is other. In this case, we're going to say the round trip also one way, 200 miles on average to these land application sites, and we're going by truck. In this one, main category is landfill, and I'll show you that we have 4 subcategories for landfill. And these are based on the EPA WARM model for landfilling. Typical is sort of the average of what we see in the US at this time. Worst case would be just a big hole, filled up, no gas collection system. Aggressive and California regulatory have both different levels of pretty aggressive capping and methane capture systems. And then in our last one, we're using the same thing, but let's show you as we go through it, if you make some adjustments to some of these, how big a difference it might end up making. Okay, and we are at, well, I'm doing all right. Okay, on the conditioning page, essentially, you know, we've got, these are automatically filled in. It knows how much biomass we're going to be conditioning. We had put in the 1% up front. And so this is the amount of dry mass per day that we're conditioning. We've got two types of thickeners in there, but this is the type of thing, and this refers to, this is going to change the polymer use and the electricity use. But we're just going to choose other, and based on the other, these two values, for polymer use and electricity use, will come up. So this is what I'm talking about. This when I was talking about the blue inputs they're up there as suggestions. There are default values in case you don't actually, as a treatment plant operator or engineer working with the treatment plant, don't actually have your own values for this. You might know the polymer use on a daily basis, but if you don't, we've got a value there for it. And instead of, this is what Janine was referring to, instead of typing that 137 in, my suggestion is to always reference that cell in case it changes somewhere down earlier in the line, and it's gonna know that you want to use the default value no matter how that changes. And it's the same with electricity use. So we have a default value for that. If you happen to have it, it's always better to use the information you have. Okay, so I'm just going to do the same thing with this one. I have the other two filled in already. And for those of you that are whizzes on spreadsheets, there are probably some shortcuts that you'll be able to find that I don't know about. Good. Okay, so on the anaerobic digestion worksheet, remember we had two scenarios. That was 2 and scenario 4 that both actually do go to anaerobic digestion. This is one of our more complex worksheets. So a lot of this is auto-filled already. The amount, the volume that's actually going to digestion, the dry weight of that material, and the volatile solids content that we input earlier. All of these cells, though, they're orange cells. You could put in something else, your own value, if somewhere along the line you found that you have better information. But for now, these have been calculated based on earlier information that we put in, like the solids retention time, all of that. The biomass quantity, then we have a suggestion, default value based on what we've input earlier, and we're going to use that, and I'm going to reference that cell. Now, here's where it's very possible, depending on how nerded out your engineers are getting about digestion, that you might have better data. We have, based on that 50% volatile solids destruction, we know we have a default value that essentially takes that amount of volatile solids that was destroyed and gives us a biogas yield for that. And that's this value. So I'm going to reference it here because I don't have any better information. And based on that, we have a default value for the methane content in the biogas. And I forget what it is. I think it's 60 from, you know, a reference that we got a while ago. So I'm going to use that too. But you might know exactly how much methane you're generating there. In this case, we can look at a few different ways of what happens to that biogas. We can look at simply flaring. We can look at use in a boiler. We can look at combined heat and power engine, CHP. That's what we're going to look at. But we also have put in the ability to look at direct injection, cleaning up that gas and injecting it into the renewable gas pipeline. So I'm going to say in this one, combined heat and power use, yes. And the total amount that we're combusting, this is important because during combustion, you do get some fugitive methane. We're estimating in our little scenario here that 90% of the biogas generated is directed to that CHP engine, with the remainder either flared or thought fugitive emissions. And in terms of the efficiency of that combustion, how much methane is lost during the combustion, we're going to say normal, but we have a couple different default factors in there. The amount of that combusted biogas is generating heat in our combined heat and power engine. We have defaults for both that and electricity. And we're not going to the renewable gas pipeline. So that's 0% is going to that. Type of flare, we're going to use candlestick here, inefficient, fair amount of lost methane for that. And the amount flared, we're saying is 9% because we sent 90 to CNG, CHP, and that makes 99% of it, the sum of those two, which is added up here, going to combustion, and that leaves 1% that we think of as fugitive emissions. We're going to use, based on that amount of biogas that was converted to heat, we have a natural gas equivalent, essentially a credit, and then we have the same thing for the electricity coming from up here. And then we've got heating requirements. Now, this is one where I don't feel like the default values are necessarily good because it's one value for the whole country. Obviously, heating and electricity requirements of the anaerobic digestion can change quite a bit, but we have default values here in case the plant doesn't, for both the heating requirements of that digester, and these are both based on that solids retention time. And then, so our net natural gas used is 159 cubic meters per day, and we generated essentially a credit in terms of electricity. And so that's our final value for the anaerobic digestion process. You can see if we made a couple changes here, like we went to default, or say enclosed for our flaring, that would make it that much better. If we assume that there was no fugitive emissions, that all of it went to combustion, then that obviously would improve, because if you lose a little bit of methane along the way, it can make a big difference in your process. Let's go now to thermal drying real quickly. This is on our fourth scenario. We know how much is going there. This is essentially, if we're going from 25% solids to 94% solids, it's a very simple equation that we have in here for evaporation of water, energy required. Plants may well have better information on that, but this is what our default value is. So this is just a calculation, but this is the amount of natural gas used to get to that point. And we're going to use that default value. I'm going to reference that cell. We have a default value for the electricity use of that as well. So here's our total greenhouse gas emissions in milligrams per year, metric tons per year of CO2 equivalents for that part of the process. Let's go now to composting. I'm going to do these. I can see them getting behind. Do this quickly. But up here, if we choose aerated static pile, this is going to fill in automatically because we had put that in the amount destinations page. In this case, it has not been digested prior to composting. That makes a big difference based on what the feedback we got from the scientific review team and the algorithms now in here on nitrous oxide emissions during composting. So we're saying no, but the level of aeration is well aerated. I can tell you that for any biosolids treatment composting facility that's meeting regulatory requirements, that's going to be the case. This is more an issue for big composting facilities that don't necessarily have those requirements and might develop significant anaerobic pockets in the material while composting. There's the amount of amendment that goes in there that makes a difference on energy requirements. We're saying we have amendment grinding on site. We're using sawdust. We have sort of a default density in there for the sawdust of 250 kilograms per cubic meter. So this is what Romy mentioned. This in the past, we automatically just determine that the nitrogen and phosphorus from compost that's used as a soil amendment ends up being a credit. But you have the ability to use that or not here. Let's just say for the nitrogen, yes, but for the phosphorus, no. This has to do with running the facility and grinding. Oh, sorry. Grinding amendment on site, a little fuel use for that. Electricity requirements of the aerated static pile we have default values for. Now here's a big one, is carbon sequestration. Very controversial issue, huge range of values that you see in the literature. And we have decided this time around to, instead of having one default number, having a range in there. For the low end would be for sites that receive material but might have relatively intensive or conventional tillage. Maybe they already have pretty good organic carbon in the soil beforehand. Mid-range would be going to a site with low organic matter where the management of that site is such that it won't be tilled or aerated regularly, maybe a no-till field. That would be our mid-range. And our high end is reclamation sites where there's essentially no organic matter on site, and adding the organic matter is going to kickstart a sort of a ecosystem there with a higher organic carbon. But for this purpose, we're going to use mid-range. And so that's our footprint of just that composting portion of this. And important to remember, this is just following the biosolids, not including greenhouse gas emissions related to the amendment in there, just that same dry tonnage of biosolids. And I am getting towards the end. We just, the land application is very similar to this one. I want to look at landfill disposal. We've got two scenarios here. A lot of this is auto-filled. I'm sorry, it's scenario 3 and scenario 4 going to typical landfills. I'm going to use default values for the methane correction factor and the percentage of methane used to capture captured methane that's actually being converted to electricity. We're saying 50%. In this case, the level of digestion, our scenario 3, it was raw material. It makes a big difference. A lot more potential for methane to be generated after landfill. And because we're in New England, we're a cool, wet climate. We use those same values for our 4th scenario, which is the same, but the material's been both digested and dried. So here you can see a big difference. Landfilling, we know, huge methane emissions from it. If you digest that material and capture that sort of more readily degraded material that goes to methane during the anaerobic digestion process, you have a lot less potential for methane from that material once it's landfilled. So this all makes sense. Digesting that material helps reduce that quite a bit. And in this case, when we look at the summary results, it more than covers the energy and greenhouse gas emissions that go into drying that material. Also, if one of these, let's look at that, it's 20,000 in a cool, wet environment. If this happened to be in a cool, dry environment, Alberta or something like that, it'd be quite a bit less because more of that methane would be generated after the final capping occurs and actually sequestered in the landfill. Landfilling, anaerobic digestion, composting, land application are really the more complex portions of this, where my time's running out, but I just wanted to show you. There's a page for transportation here. Mostly you can
You
get
got
the,
5 minutes, Andrew,
okay.
at least. Okay.
Mostly you can get this information from the amounts and destination page, and it will give you a total greenhouse gas emissions for the portion that's dedicated to just transporting that material. As we've said in a lot of presentations before this one, transportation is usually a really small percentage of the total greenhouse gas emissions, because methane and nitrous oxide have such high global warming potentials that a little bit of them sort of mask a lot of the direct CO2 emissions from burning fossil fuels to transport that material. So the final page, kind of the final results, is the summary page. So you can see for all the different areas that we included, oops, sorry, I need to go up a little bit. For all the different unit processes we included, for each of these scenarios, we have a number associated with it, greenhouse gas emissions. This essentially sums it all up. That is the total for our 50,000 tons managed in New England, total greenhouse gas emissions per year in the form of CO2 equivalent, metric tons of CO2 equivalent per year. This also breaks it down into the different categories, CO2 versus methane versus nitrous oxide emissions. We do, as is required in most greenhouse gas emissions accounting, we actually calculate the amount of biogenic CO2 emissions that come up, but those don't get added into our actual greenhouse gas footprint because they're considered biogenic, not a cost or debit. And so here's the actual numbers per year. Obviously, our landfilling scenarios are much higher. Compost and land application tend to be a lot lower. If I didn't show you this, but in land application, I'm assuming that this is in a humid environment where we do have some nitrous oxide emissions associated with the actual land application. If this were an arid environment, or if it was thermally dried biosolids, this would look much closer to the composting one. But both of them are, as you can see, considerably lower than taking them to a landfill, because you have that avoidance of methane. Often look at this number, which is the CO2 equivalent per dry metric ton. It's a good one. It's a little bit, if the material gets digested, it's actually a little misleading. And sometimes because after we've digested it, we have less wet tons of that material. We've lost all those volatile solids. Sometimes instead of, you can't see this, instead of dividing this total by the wet tons after digestion, I will actually divide it by the wet tons before digestion, because that's a more direct comparison to get this number. But this does give you a pretty good feel of, like, yeah, it, you know, some of these things are just, oh, you know what, here, I've still got this landfill one, undigested landfill on cold dry, so it's showing to be lower than this one. But remember, this was actually 20,000 or so it's quite a bit higher than the anaerobically digested and thermally dried one. So I'm going to end it there.
All right. Yeah, we have,
Yeah.
Bill was going to show some examples of using it, but we do have a question already. Oh, it looks like folks were answering it in the, oh, Bill, thanks. But maybe you could just, since you're up, Bill, just basically summarize what you said, because this is a great question. Your thoughts on whether we should use 20 or 100 year. I think we have a 25-year and 100-year options in the beam, but
20 and 100.
20 and 100. Okay.
Yeah, there are various standards, but I think for any kind of greenhouse gas reporting, you're going to do 100 is the typical standard. But Chris, you're totally right. Which one you choose has significant impacts, particularly if you have methane emissions, because it's a shorter lived greenhouse gas in the atmosphere. So, you know, carbon dioxide goes up and stays for, you know, centuries. methane goes into the atmosphere, but degrades over time much more quickly over the order of decades. So using 100-year global warming potential can kind of mask those short-term effects and potentially the short-term benefits you can have from addressing, say, for our purposes, say, fugitive methane at wastewater treatment plants. So I think in general, for any kind of official accounting, whatever you're going to be doing, probably stick with the 100-year. But it can be intuitive, or it can be instructive to look at 20-year and just say, okay, look, we have potential for a lot of bang for our buck by addressing these short-term climate pollutants.
Yeah, good point. All right, I think the next slide is
Yeah, I was just going to go over some other greenhouse gas inventory tools that are out there quick. One in a bit more depth, but I just wanted to mention some other ones. We're of course partial to BEAM. I think it's kind of the gold standard when it comes to greenhouse gas accounting for biosolids treatment and for management of biosolids products. But there are other ones available, particularly if you're doing kind of more broad wastewater treatment. You know, your full wastewater treatment plan or water resource recovery facility. There are some others that can give you a broader look that are available. Again, like Andrew said, Canada's or maybe Janine, Canada's way ahead of us. Europe's ahead of us on a lot of this stuff. So there's a couple of publicly available tools. The ECAM tool that I'll talk about a little bit more. There's another one, Ontario, the wastewater folks there have put out a greenhouse gas inventory tool. That's the second link there. There's one out of the UK that has, it's broadly looking at wastewater treatment. And then there are some that are more specific to things that may or may not touch on your plant. COMET is kind of looks really specifically at like what are when you're land applying organics, what are the impacts there? The American Biogas Council put out the Biogas CAT carbon accounting tool. So if you have biogas emissions, this is not just for wastewater treatment plants, also manure and food waste, but you can look at that to get a better idea of emissions associated with digestion. There's the GREET model that is used to determine some of the funding for Inflation Reduction Act, if that still exists. And there's a couple that aren't really publicly available. I just wanted to mention there's one out of France, Just a View, and then Black Cat was developed for a particular facility, but might be kind of helped to be incorporated into BEAM over time. And then, there's custom-made models that various folks have. So if you go to the next slide, I did want to mention one other thing is this WRF project that's ongoing, hopefully completed early next year, got a little extension, but this is a project where a bunch of folks that are active in the industry are looking to establish kind of industry-wide guidance for accounting for greenhouse gas emissions from water resource recovery facilities and beyond. So that's keep an eye out for that. It'll hope to give some guidance. And then so ECAM, I wanted to talk a little bit more about this. This is unlike BEAM, which is a Excel-based tool. ECAM is a web-based tool, and it allows you to do a greenhouse gas inventory, look at different alternatives. A lot of things you're able to do in BEAM, but it's not just specifically for biosolids, it goes a bit beyond that. So fairly intuitive interface. If you go to the next slide, it is much broader. So everywhere from drinking water abstraction and treatment and use through wastewater collection and treatment, and potentially even on-site sanitation. So you could do, if you're a water wastewater utility, you can use this tool for kind of for a broad range of things. If you click the next slide, so there's under each one of these, wastewater collection or treatment, there are kind of these sub modules similar to BEAM, where you're putting in whatever data you have. It's very similar to BEAM, where there are suggested values. You put in your population, and it says, okay, our typical estimate would be, this amount of wastewater is generated from that population. But like BEAM, you can customize it if you have more exact data. Always better to use, measurement-based emissions factors as you can, and your particular plant data. And you can see there's, you can specify whatever treatment you have on the plant, and it'll help you to generate your inventories. If you go to the next slide, it shows down to what kind of we're interested in here with the BEAM model, and actually some of the things in here reference the BEAM model. But when you're looking at sludge management, when you're looking at biosolids management, you can look at composting, incineration, land application, landfilling, all these things, and there are emissions factors that are associated with that that are built right into ECAM. And it's nice, it spits out these graphs. You can download your data and kind of put in whatever form you want, but it's just kind of a nice one-stop shop where you can pretty high level put in your data. It gets down to a decent granularity. You can customize it as much as you want. And then it'll spit out some kind of compelling graphs on the back end that are broken out in different ways. So just wanted to share that there are other tools out there that folks can use. And I wanted to touch on one example of how I've used Beam. So going back to Beam, we did for Massachusetts, we did a statewide study looking at kind of how biosolids are managed in the state, and then we're looking at kind of where things might go in the future. But one of the things we wanted to look at is the greenhouse gas impact of what they're doing currently with their biosolids management practices within the state. So we knew where all the biosolids are being generated in the state and where they were going. If they're going to landfill, if they're going to a compost facility, if they were being dried and land applied, if they were being hauled from one plant, typically a smaller plant to a larger plant, various things. And so we took the statewide data and did the calculations in Beam that Andrew was showing. Typically you're doing it for your own facility, but here we're just aggregating all the data, and we had the hauling miles and everything. And we were able to calculate the both the greenhouse gas emissions and any sequestration value that we had, and then get the net, that's the kind of yellow diamond there, of different approaches to managing biosolids. Is there another slide after this, Jeanine?
Yeah, this one is my example, and the next one is Baochang's example. This was done by the Beam team, and just taking a look at what's going on in Maine and a particular facility in Sanford that's gone from making a beautiful compost product to still composting to stabilize it, but sending it to landfill and or combustion in Canada. And then the next one is very interesting. I don't know if Baochang can explain this one.
Yeah, very similar to the example that Bill provided. We were tasked by Water Corporation that in Western Australia to kind of help them look at potential emissions from all these thermal treatment technologies that they were very interested in implementing one to deal with the PFAS issues. And then so essentially we look at comparing the pyrolysis and gasification and incineration that will be operating at different temperatures, because that was one of the key criteria for nitrous oxide emissions from the incinerators. So, but of course we were just comparing it, and then we make site-specific assumptions, and so hopefully this can show you a fraction of the versatile tool that Beam can help you with process option selections.
Yeah, I'm always interested in how folks are using it. And there was a couple of questions, so we'll just put this up here now, but this is where you can download the spreadsheet. Someone was asking about cost. Yeah, it's a sliding scale. Engineering companies, folks that are going to use this for their work, it's $800, and then it goes down from there. Small nonprofits, educational facilities can get it for free. We just really want you to use it. But if you do donate to pay, which will help us maintain this process for reviewing it and the website, you'll get a code so you can unlock the spreadsheet and make it your own. And also some examples, 10 examples that Andrew did for us that can really be helpful when you're starting out using the Beam. I think that's all we wanted to say on that. Are there other questions that maybe we didn't get to yet? Here's another one. We already did that one. Oh, any resources for emissions for post-digestion storage lagoons?
That's a really good question. We do have storage in here, and there are a couple options there, and they're simply related to whether or not it's aerated and the depth of the lagoon. So that would fall under the category of something that we don't have in there, but because we already have the storage unit process, if you had an idea of what the emissions might be coming from that, they'd obviously be lower if they were digested beforehand, because methane is going to be the biggest one coming from that, and even your nitrous oxide emissions will probably be reduced a little bit after digestion, just like they are during composting. You could put that in. But we don't have that in there at this time. It's one of the things, as every year when we do or every other year when we do the scientific review team, we try and find those things that either aren't in there yet, or we know the information isn't robust yet in terms of backup. And so as we move along, if we find more people don't are in that situation, we would look to a scientific review team to develop standards for that. But for that one in particular, we do not have that.
Well, I'm making a note of it. And yeah, as Andrew mentioned, like going forward in the future, we are looking to, add other processes. We're going to primarily be focused on ones that are in operation now, not like SQO or some of these evolving processes. So any suggestions that you have would be welcome. I have another question here from Canada, I think. A previous version of BEAM applied conditioning and thickening to all sludge, primary and secondary. Is it still doing the same? Have there been considerations to separate those? Also,
No,
has there been consideration to include co-digestion? Yes, we've thought about that.
Okay, so yeah, as two sort of different questions, and for the first one, no, we don't, and what we struggle with sometimes is the granularity. I mean, it's one of the strengths of the model is it has a lot of granularity. It's also a little bit of a weakness because it makes the model that much more complex and makes the fill-in data harder. So, but in that one, it's a good example of like, so we've got default values for conditioning and thickening. And they don't separate between primary and secondary, but that's the kind of thing where the two costs are electricity and polymer in terms of greenhouse gas emissions. So if you have those values, you would put them in yourself, and it's going to be a lot better information anyway. Oh, and the second one,
Yeah,
co-digestion. So it's a good question, and I've used the model quite a bit for clients that do co-digestion. The one thing is like that's tricky there is the boundary. This is really following the solids process through the wastewater treatment plant. So it's sort of specific to sludge coming from that wastewater treatment plant. We've used it for food waste, and it actually has the algorithms that are necessary for that, but it's just an area where you want to keep, you want to be careful about, what boundaries you're using, make sure you're not double counting somewhere. But yes, it can be used for that.
Great. Thanks, Andrew. And this one's going to be for Bill, I think, in terms of biosolids emissions. Do we know what are the main different assumptions from BEAM and the ECAM?
Yeah, I don't know like side by side exact comparison, but my memory is that the nitrogen and phosphorus offset in ECAM references BEAM. So you get a credit in BEAM for basically not using inorganic nitrogen and phosphorus and the greenhouse gas emissions associated with their production. And at least the last version I dug deep into in ECAM, it was referencing BEAM for that. The carbon sequestration value is different. Again, I'm not sure what they have in there now, but it's different than what BEAM is using, particularly the most recent version. And then, the electricity grid is just different in Europe. It's a Europe-based tool, but of course, you customize it to your own e-grid, to your own emissions from your grid. But the big ones are the carbon sequestration factor. There would be a big difference between the two.
All right.
And
Thanks,
I'll
Bill.
just mention, following up on what Bill was saying in terms of the e-grid, you don't have to choose an e-grid value for the carbon intensity of electricity. We do have a spot in there for user defined. So we've had some facilities that, now have a certain greenhouse gas intensity or carbon intensity that goes with electricity, but they're looking to use more renewable in the future. So you can put in that value of, what you predict it's going to be in the future, and it'll change throughout the model, the electricity cost.
Yeah, it's great how customizable it is. But we are out of time now, and I know we went through a lot, but I'll share the slide deck and the recording with everyone who registered next week. I want to thank Andrew and Romy and Haley and Bill and Bao Chang for all your help with preparing this webinar. And thanks to everyone for attending. Next month, we're going to lunch and learn about the Water Research Foundation's project number 5107, looking at the fate of PFAS through gasification. And as always, if there's something you want to lunch and learn about, please let me know. I'm always looking for suggestions. Thanks again and have a great long weekend, everyone. See ya. Bye.
Right.